So looking at page 33, we're talking about counting principles, factorial, permutations, and combinations. So the first example, a group of 3 people must be arranged in a line. How many possible arrangements are there? So we start off with 3 people, call them A, B, and C. Any of the 3 people can occupy the first position in the line. Once we've placed one of those 3 people, let's say we place A. Now we're down to B and C. Then we have a choice, are we going to place B or C? So let's say we place C. Now we're down to just B as the final individual that could be placed. All right. So with that in mind, we have any of 3 possibilities for the first position, any of the 2 remaining people for the second position, and whoever's left over would occupy the third position. That's known as a factorial in the sense that if you take a number and multiply it by consecutively lower and lower values until you get to the number 1, we can represent that as a 3 with an exclamation point and use technology, for example Desmos, to run that computation for us. All right. In the case of 3 times 2 times 1, we wouldn't necessarily need technology, but if you had something like 19 factorial, of course, you would want to use technology for that. All right. So we have, or I typed in an example here, 5 factorial, just to give you a sense, but you also have the general rule, n factorial is the same as n times n minus 1 factorial. So just using that rule, I can say 3 factorial is 3 times 3 minus 1 factorial, which is 3 times 2 factorial. Then we would follow that by saying 2 factorial is 2 times 2 minus 1 factorial, which is the same as saying 2 times 1 factorial. So 3, we would carry that along for the ride, multiplied by 2 times 1 factorial. The 1 factorial, well, the end of the line is 1, is equal to 1 itself, so 3 times 2 times 1. That's a little bit more of a rigorous proof, but that's the idea behind it. So that's what we call a factorial.
A permutation, in the example that we did, we had 3 individuals with 3 slots, right? But a permutation, you're restricting the number of slots that are available. It's kind of like musical chairs. So you have 5 individuals, but only 4 chairs, right? So we want to know how many ways the people who are participating in the game could end up being seated, when the music stops. So when you look at the structure of it, in a lot of ways, it's very similar to what we just did. In fact, I'm going to do a fair amount of copying and pasting. And what I mean by that is I'm going to do like almost all copying and pasting. And then I'm just going to trim out a couple of things. Right? So instead of having 3 people that are going to be arranged in 3 slots, I'm going to have 3 people arranged in 2 slots. Right? So that would eliminate this stuff. But virtually everything else is the same. So not too much different in terms of the way we write things or the way we would carry out the process. Right? So any of 3 people could occupy the first position. So it's still the same what if scenario where I'd look at it and say, well, I have 3 people to work with. All right. If the first person selected was person C, then that means that there's only 2 people available for the second slot, right? So that's as far as we would get. We could also kind of think of this as really the same question as the factorial, because it's really the same underlying logic. Because if I say that I'm taking 3 people and I'm lining them up into 3 different positions, position 1, position 2, position 3, that's the factorial. 3 people, 3 slots. 3 people, 2 slots is really like, all right, any of the 3 could be in the first position, any of the remaining 2 in the second position. Anyone left over, take a walk. Get the hell out of here. Right? You still have to deal with the fact that that extra person exists. They're just not part of your plans. Right? So you say, all right, any of the 3 here, any of the 2 there, the one left over, bugger off, get out of here. Right? That's really all we're up against. It doesn't always play out that way, but when you're dealing with a permutation, it often does. Right? But the notation is kind of interesting. The way we would write it, so that's 6, instead of saying a factorial, we would write 3p2. Right? The P stands for permutation, so that part should be easy enough. But the 3 is the number of individuals available. So I'll say number available. Number of slots. And I'll actually be a little bit more specific. I'll write the individuals. I don't want to say people, even though oftentimes individuals implies people. In statistics, we use individuals to the term individual to represent the singular, right? So an individual could be a single chair, a single flash drive, a single TV, a single cough drop. You can tell I'm just looking around my room here to see if I can come up with ideas, but that's really it. So how do you get this on a calculator? Because if you had something like 3p2, that's not a big deal. And I don't want you to get the idea that 3p2 means 3 times 2. I would ask you to kind of question that and say, if 3p2 meant 3 times 2, why the hell would we need the notation of 3p2? What would be the point? Right? It has to mean something more than that. That 2 after the p is talking about the number of positions available. It's just coincidental that it happens to be 2. Right? But if I had something like 99p50, I'd have to draw out 50 slots, start with the number 99, and then decline or decrease from 99 by consecutive values, 98, 97, 96, 95, until I've used up all those spots, and then I'd have to multiply. That sounds terrible, right? So instead, on our Desmos calculator, we go to functions. You have under stats the option NPR. So you bring up the function NPR and then type in 3, 2, and it'll just spit out the value, right? So the issue that we're always going to run into when it comes to technology is sometimes the math way of representing a computation and the way technology accepts it is slightly different. And so we have to make that adjustment. So we write it on paper as 3p2, but on the calculator on Desmos, it's NPR 3, 2, right, on Desmos. All right. So when you see something like 5p3 in that example that I have below, this guy right here, On Desmos, it would be function stat NPR 5, comma 3. Close it up and you get your 60 out. Right? So it's not too bad at all. Let me check the old chat here. Permutation. Yeah, so that's what it stands for. Yeah, no problem. So the formula, NPR equals n factorial over n minus r factorial. This is a more mathematical way of doing it, but it's also kind of interesting. I mean, it's definitely very interesting, but you kind of have to be interested in the math behind it in order to find it interesting. So it varies from person to person. But let's say I don't have an equals yet. Let's say I have 3p2, like the example above. That would be the same. You can see the ends occupy consistent positioning. And, this is like a little nostalgia for me because this is how I learned it back before calculators existed. No, that's not true. I found out that that graphing calculators existed long before I started going to high school, because none of my teachers knew how to use them until my senior year. That's not true. Maybe my junior year, but still, it was like the end of the line. So it was like all those years I could have been using this stuff. Desmos wasn't even a thing. It was a dream at that point. So 3 minus 1. I'm sorry, 3 minus 2. This technique relies on you having a sense of factorials, but that shouldn't be a problem. Factorial is the easy part of this. So 3 factorial over 1 factorial. 3 factorial is 3 times 2 times 1. 1 factorial is just 1. So 6 over 1 is 6. All right. So you can get it using a formulaic approach. You can get it on the calculator. It's kind of a fun endeavor. It's more puzzly kind of experience when you're doing it by hand. But you always have the ability to go back to the calculator. That part's up to you. So that's what a permutation is. It's a limitation of a factorial. All it's doing is it's really just saying, okay, we're playing musical chairs. We got 20 people. We got 18 chairs. We got 15 people. We got 5 chairs. Like who's going to win? How many ways can they win? That's the permutation. Now, a combination, which is what we're going to get to in a sec, that's limiting it even further. Right? The key word when it comes to factorials and permutations is the word arrangement. Right? So anytime you're arranging something, you're talking about factorials and permutations. But whenever you're talking about grouping, you're dealing with what's known as a combination. But let's kind of take this, as its own example without getting into formulas and stuff like that just yet. So we have 5 students in a class. So those students are A, B, C, D, and of course, E. We want to determine the number of 2-person groups that can be generated from the 5 available students. Right? So one way of handling it, and like if you're a teacher in a class, you might actually do it this way. You're not thinking to yourself, all right, well let me get the old calculator out, the old Desmos calculator, and run some numbers here. You're probably thinking, all right, I'll put Sam and Jackson together. I'll put Christina and Michelle together. I'll put, and just go down the list there until you've used up all the individuals in the class. Now, you're probably not even doing it randomly. This assumes that you're at least taking into account the possibility that randomness would be a thing, right? Because you take into account personalities. Like these 2 people don't work well together. These 2 people work really well together. But if you're doing it in a really random sense, then you might consider doing something like making a tree diagram. That gets a little lengthy, depending on how you construct it. But you go a little simpler and create a sample space. And that sample space would be saying, all right, I only want the unique pairings of individuals. Because if I tell you that we have Charles and Billy in one group, and then I say, okay, that's group number one. Group number two is Billy and Charles. Say, well, wait a minute, you already got them. You've already counted for those people. So I can't say B and C is in one group and then turn around and say C and B is in another group. It's the same group. It doesn't matter what order the order in which I select them. Right? So what I would do is I would just go through and identify the unique grouping. So start off with A and say, okay, who can A work with? Well, A can work with B, A can work with C, A can work with D, or A can work with E. A's not going to work with him or herself, so I wouldn't include that. Right? Then I'd move on to B and say, okay, well, who can B work with? Well, I normally would say B could work with A, but I already got A and B paired up. That's already a possible combination. B can't work with him or herself because I have to have two unique people per group. So next up would be B and C, and B and D, and B and E. So there's only 3 different combinations that involve B with someone else aside from who they've already been paired with, right? So then I'd move down the line. I'll just move this over and say, okay, who can C work with? And say, well, C can work with A. Oh, wait a minute, already got that. A and C. C and A, same deal. Right? How about C and B? Well, I already got B and C, B and C, C and B, same deal. So C and D, C and E. All right. So then I look from the perspective of D. And I'd say, all right, well, who can D work? D and A, got it. A and D, same thing. D and B, got it. That's the same as B and D. D and C, C and D, same thing. D and D, well, D's the same as D, so that's not going to fly. How about D and E? Ah, that's a unique one. So D and E. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different groupings. So if you're thinking to yourself, there's got to be an easier way, number one, or whoa, all that, and there was only 5 students. I hope he doesn't ask us for 10 students or 20 students or anything like that. Some combination of 2 ideas is where we're going, right? Because, yeah, I'm going to ask you for cases where there's more than 5 students, and yeah, there's an easier way, right? So let's take a look at a permutation and see how that compares. So if I were to say, all right, I got 2 people per group, I might look at that and say, okay, that's 2 slots. Right? So 2 slots, meh, and then an additional meh, so 2 mehs. Any of the 5 people can go in the first position, so 5. Once I occupy that position with one of the individuals, there's only 4 people left for the second slot. 5 times 4. Well, that's going to be a 20, so that can't be it. But if you look at the relationship, if I can get the dang point to work, that gives you a result of 20. Compare that to what we came up with, and you start thinking to yourself, hopefully, oh, well, that's exactly double what we should have. Maybe I just divide by 2. Maybe it's a permutation divided by 2 all the time. That goes back to the idea of permutations versus factorials and things like that. If it were that simple, we would not need a new word for it. It would be, okay, well, sometimes you divide your permutation by 2. That's not what's happening here. Close though, right? If you think about it, A and B had a corresponding BA, right? If we flip the order, we could say A and B, B and A. We disregarded the B and A because that was the same as A and B. Same thing with the C and A, the D and A, the E and A, right? The C and B, the D and B. So all the reverse values, we eliminated that because it was overkill, right? So it's really just a question of figuring out how we can divide out the overkill. So what we look at, because I need to know what this is going to be. Let me make it a nice looking box here. That is not a nice looking box, for the record. So divide by 2. We know it's supposed to ultimately end up being equal to 2. All right. So it's just a question of what it was that led to that 2. So the skills that we've learned so far involve permutations and factorials. All right. So maybe, well, we've already used a permutation. Maybe it's a matter of using a factorial. So what I would look at is the number of different ways that I can arrange 2 values. Right. So let's say, for example, I'll just kind of put it off on the side here. We have A and B, B and A. Right. So that's from the letters A and B. I'll put a comma there. Those are the different ways that you could arrange the letters A and B, right? So if I tell you that I want to line up 2 people, Tommy and Joey, right? Well, it could be one arrangement, Tommy in front of Joey. Could be the second arrangement, Joey in front of Tommy. Right? So that part's of it. Right? We could do it for other possibilities. Maybe we could say B and C, right? If I have the letters B and C to work with. It could be B first, then the C, or it could be C first, then the B. Right? So these are our possibilities. So in each case, it seems like there's 2 arrangements. Right? And that's going to be the same for every other case. Any other pairing of letters, there's always going to be 2 ways in which I can arrange them. All right. So 2 arrangements, 4 qualities for the exact. 2 arrangements per pair of letters. All right. So then it would beg the question, all right, how can we get that number in an easier fashion? Well, the easier way to do it would be to say, well, I have 2 things and 2 slots, really, because I have a slot here and a slot here. Here's my first item, here's my second item. Any of the 2 items can go in this position. Whatever's left over can go in that position. It really ends up being 2 times 1, and that'll give you the 2 outcomes that we're looking at. So if I were to say that I want to take 2 letters and determine the number of ways in which I can arrange them, it really is just 2 factorial. Right? So that's just going to be 2 factorial. So then it begs the question, so 2 factorial, 3 dots in the form of a triangle just means that. Right? You write the word out. So that's telling me that the bottom of my fraction should have been a 2 factorial. So what we want to do here is really kind of generalize this. All right. I don't want to have to do all this work every single time. If I do it every single time, then it's a waste of time. We want to generalize. All right. So what I'm going to do is I'm going to say, well, the top seems to be, well, 5 things, 2 slots. That top seems to be 5p2 based on what we just learned above.
I want the gloves.
Right? Oh, I thought there was a question. No?
It's standing. Oh, sitting. Laying.
Didn't do it that way. The 5p2 gives you the top. The bottom just seems to be 2 factorial. So then you just kind of look at the numbers that were given to you in the original problem and see if there's a way that maybe we can generalize that to a more universal way of doing things. And that's where the next page is going to come into play, right? Because a lot of this is the theory behind it. We're building towards an understanding. But yeah, like it's what I've been saying. I mean, yeah, you want to understand it, but you also want to get stuff right too, and you also want to streamline it, become more efficient, and so on. Worst case scenario, you got that diagram there. That'll get you your answers. It's not. I mean, I made it look kind of nice, colorful, and all that stuff. But I was going to say it's not pretty. It's not something you're looking forward to. It'll take a while, especially if there's more than 5 students, right? But if I tell you that there's a nice little shortcut that'll crank this all out for you, as long as you recognize a couple of key words along the way, that'll help. The key word is group, but more so, it's an intuition. The fact that we're not dealing with an arrangement. I don't care in what order the individuals were selected. I just care that they're selected. Now, you just kind of imagine you got a handful. Your arms are filled with like groceries. You're coming home from the supermarket, or you got books. You're just walking down the hall of your school, whatever. You're just loaded for bear. You got all this stuff in your hands, and you just need a couple of people to help. Hey, can a couple of people help me? Who do you want to help you? I'm like, oh, thanks. Don't all jump up at once. And it's like, oh, okay, Tommy and Jimmy. Well, Tommy then Jimmy, or Jimmy then Tommy. I don't care. I just need the 2 of you. Come on, let's go. Help. That's a combination, right? But on the other hand, if it's like Tommy and Jimmy are running in a race, and first place gets you a flat screen TV, and second place gets you a $5 Dunkin' Donuts gift card, then it does matter in what order they're selected. So, that would be an arrangement, and that would be a permutation. Right. So this whole computation, which ultimately ends up giving you the 10. Oh, that's not a 10. That's going to be in a shorthand way of representing it. And I'll resize a little bit. We can write that as NCR, which is a combination. I'm stealing my own thunder a little bit. I'm just going to move some things over. Just going to move some stuff around. So this would be 5C2, but it follows the formula or the model NCR.
Now it's gonna be our third, yeah. This is our third coming up. We did 2.
Christ almighty. So go into my handy dandy Desmos calculator. NCR, I'm going to type in 5, 2, and we get our 10. All right, so like in terms of typing the values in, you're going to get, or at least you're going to follow the same process that you would for a permutation. You just need to know under what circumstances you're using a permutation model, the NPR, versus the combination model, the NCR. Right? So the term itself that you're looking for, really, if you kind of bring it down to brass tacks here, you're looking for groupings, because pretty much everything else is just going to be an arrangement. Right. So if you identify that it's only the groupings without the order being important, the case where you have an arm or 2 arms filled with groceries and you just need a couple of people to help you out, doesn't matter what order they come to help you out, that's going to be a combination. Right. So I'm going to flip it over to the next page. and we're looking at number 4, 5 students are in a class. Exactly. NPR is arrangement and NCR is for grouping. Yeah, you live long enough, you see everything, I guess. It's really kind of fascinating. I'm just kind of like mesmerized by this. Are they lifting weights? Is that what's going on there? I don't know. I don't know that I need to see that. Uh, uh, I don't know. I can't even tell. Is he even going to do a rep?
Oh yeah.
Balancing it? I got nothing. Hard to tell. So, there we go. So, I mean, hey, we all make it work somehow, right? 5 students are in a class. Determine the number of 3-person groups that can be generated from 5 available students. Right. So we're looking at really the same idea, and you can see below we're kind of formally getting into the concept of a combination, but it really is just kind of boiling down to the same thing again. We're just taking the 5 people and creating groups. Right. Mental rep. Very good. So we could actually work off of our previous answer, and we talked about this over the last couple of classes. Sometimes probabilities can be they can be pretty intense. You've discovered this, like there's some mental gymnastics going on. But if you can kind of find a shortcut through the maze, you'll end up thanking yourself for that. So if you really just take a second to think about it, 5 students are in a class. Determine a number of 3-person groups that could be arranged or generated from the 5 available students. So what I'm going to do is I'm just going to grab my little diagram here. This diagram, and I'm going to reproduce it on the next page. And I'm going to space it out a little bit and get rid of some check marks. And after I'm done editing it, it'll be like, you could have just wrote it again. And I kind of fall into that little tug of war. So, hey, get over there. I heard it is a little bit off topic, but I heard that in Jersey City, I think it was Jersey City, because of the spike in COVID, that they're requiring that gyms specifically, because it's relevant, gyms are required to shut down every hour for a half hour for cleaning. And it's like,
wow.
So you're telling them to close, is what you're saying. I mean, that's the only interpretation. I mean, if you go to the gym, I mean, the only person that would be all right with that, I guess, is the person who's popping in at the right time for like a 20-minute workout. That's pretty insane. I mean, I guess they got to do what they got to do, but geez, yeah, right.
How did we get on this gym conversation? There's been a lifting theme for the past 5.
Yeah, one of our classmates was pumping iron in the gym there. Forgot.
Amazing. Hey, multitasking plus increases stimulation. So respect.
Yeah, it's like fresh out of dodgeball. It's like sometimes I like to break a mental sweat. White goodness. So, all fun, I guess. So, I got this diagram going here, And I got my little 10 groups there. It's such a nice looking answer that I hesitate to erase it. I kind of feel like I want to keep that. Right? So I'm going to modify my picture here. And so these are the individuals, because we talked about this over the last class or two, where sometimes figuring out what you don't want will help you figure out what you do want. Right? So if I create a group of 2, for example, a group of 2 by default is going to give us an additional grouping of 3 people. These are the leftovers, the people we don't want. I mean, it's pretty terrible when you think about it that way, but that's essentially what we're looking at here. All right. So if I tell you you got a class of 5 students, for example, and you need 2 students to run up to the main office to grab something from your mailbox. You're a teacher, you're asking them to do you a favor, and you need 2 students for some reason. You're creating 2 groups when you do that. You're creating a group of 2, the 2 students that are leaving the classroom, but you're also inadvertently creating a group of 3, which are the students that are being left behind. And really, if you think about it, maybe you're not inadvertently creating 2 groups. Maybe that's intentional. Maybe it's like, all right, I got to get rid of these 2 students. They're not the nicest people in the world. So let me give them a task to do. Let me send them out of here. And when you do that, it's like, okay, well, now that they're gone, let's have some fun. It's like, it's kind of a dark way of looking at it, but that's kind of the idea. Or it's like, I'm trying to think of a case that doesn't involve excluding human beings. I'd probably stay away from farm animals. Yeah, you can look at yeah. So let's say you have, you put out dinner, and you have an assortment of vegetables, and for some reason you quantified them specifically by you have exactly 3 carrots and 2 potatoes, and it's like, all right, well, I don't want to eat the potatoes, for example, so I'm going to generously offer those to 2 people. Okay, so here, who wants some potatoes? Oh, you could have potatoes. Here, one for you, one for you. And by doing that, I'm creating a set of 3 carrots that are available for, as the leftover. So it's kind of like a byproduct, but it's a byproduct that creates a group. So if I have a group of AB, necessarily creating the group of leftovers CBE. Same thing with AC, a leftover group of BBE. AD, that would give me BCE. And as tedious as this is, I'm still going to go through it because it's like, well, I'm really just relying on work that I did for a previous answer to help me with this one. So BCD. So long story short, I wouldn't even have to come up with this entire list in order to know, wait, it's going to be the same answer. So my good-looking answer of 10 groups, I can still keep that. I'm going to take a look at the chat in a second. I see some things there. So A, B, E, A, C, E, ACE. That's when I knew I was going to be a math teacher. When my high school pre-calc teacher and calculus, as it turned out, he called me Ace one day. And it was like, oh, that was so nice. I think that means I'm good at math. And so 25 years later, here I am. A, B. And it's funny because I have a colleague that absolutely hated that teacher. So it's kind of weird. And also just human nature where you can have 2 people that have very different experiences with a teacher, and yeah, it's how it goes. You know, humans are humans, but it's nice. It's nice when I remember someone fondly, and when they remember me fondly. Happened today when I was getting a flu shot. Yeah, yeah, yeah. I'm ready for bedtime too. Yeah. Yeah, it was kind of nice. The lady who ran the flu shots at my school was like, "My son had you as a teacher, and he thought you were the greatest." And it's like, you know what? That's just nice. It just makes my day. You know, I know I'm not the greatest, but I'm not the worst either. So it's right where I like to be, exceptionally ordinary. So, so this is what we're looking at. We got all these different cases where we have groups of two followed by groups of three. So it's just in this case we want the leftovers. We want the other guys or gals. But it's still going to be 10 groups. Right? I could have done this with a little bit of a shorter approach. We want 3-person groups from the 5 people. So 5C3 in Desmos. I know it's detailed below, but in Desmos that would be NCR 5,3. Right. So little, no, I'll just keep it there so we have a basis of comparison. Function MCR 5,3. Boom shakalaka. We got a couple of times. That's pretty nice. Right. But it also leads us to a conclusion. It's a variation of a complement rule, but it's a complement rule for counting. Right. And that tells us, so, and it's detailed below, but I'll just say it here anyway because we're kind of in the group. So we have a rule here that if you have something like NCR, right? I'm just leaving it in general terms. That's going to be the same as NCN minus R. Right? Now that's a little bit funky in terms of the notation. We don't like the notation too much. So a quick example, if I say I have something like 20C2, that's going to be the same as 20C 20 minus 2. All right. So 20C2 equals 20C18. All right. If you're wondering about the penmanship today, it's because I forgot my Apple Pencil at school. So this is.
And sorry, why are you using C instead of P here? The combinations have permutation?
Because of the fact that it's groupings rather than arrangements. Right? If we cared about the order, then it would be permutation. But because we just want the people, we don't care. It's the grocery example. Like I just need help. I just need 3 people.
Yeah.
So, and you can verify. So again, NCR, I'll do something, like a little bit bigger in terms of the example, 20C2, 190. I wouldn't want to make that list, And so, little duplicate action. Save yourself a little bit of time. And 20C18 gives you the same thing. So, it's a nice little nifty recognition that you can use to arrive at the answer a little bit quick, right? But only if you really see it. If you got to get to a point where it's like, I think that's a rule, I'm not really sure, let me check it on the calculator. You could have typed it in the calculator 3 times by the time you do that. So you don't want to really go down that road. It's really more of just like a sight recognition thing. Save yourself the time, but only if you recognize. Right? That kind of comes more with experience than anything else. When you see the examples below, these all are examples with a purpose. It's evaluate by hand and then evaluate using a graphing calculator. When you do it by hand, some of them are easier than others. So the permutation one, that's not pretty if you were to do the whole thing out by hand. But since what this is telling me is that you have 14 individuals and 14 slots, so I could actually just do that real quick and then follow that up by saying that I would never do it this way. But 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So then 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. You do that one time and you realize, oh, wait a minute. That's the same as saying 14 factorial. So instead of writing all that stuff out, I could have just gone with 14 factorial, because whether you multiply 14 factorial out, like we listed it out here, 14 times 13 times 12 all the way down to 1, or if you type 14 factorial in your calculator, I'm not going to know the difference. Right? So, oh, I forgot this is the one that we just looked at. So that would be the lovely answer here. That being said, when you look at an answer like that, there really is no expectation that you would put that answer down for anything on a test, because it serves no purpose. You look at 8.717, blah, blah, blah. That's an estimation of the true answer. A lot gets lost when you move over the decimal point 10 units to the right. You're going to have a couple of zeros at the end that are really just approximations of the true answer. So this, even though it says by hand, this is actually a better answer than the true decimal answer, right? Because there would be an overflow that would cause estimation in any calculator. And the exception would be if you were using like Excel or something like that, which you can manipulate the rounding to go out. Like if you wanted to go out 20 digits or something, you can make it happen. But it's all right to leave an answer in terms of factorials. Think of a factorial kind of like a radical. Like if you just think about any class where you studied radicals, sometimes the answer was just radical 2. You'd rather write that than 1.414, blah, 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 and then round it, you lose accuracy. So you just write the radical 2 and then call it a day, right? That's really what we're going for here, all right? So the 14 factorial kind of has the same feel as something like radical 14. Like it doesn't serve a purpose to expand it. Now, if it's something like 5 factorial, sure, yeah, that's 120. I'm going to write that. 120 is a nicer number than 5 factorial. But 8.7178291 times 10 to the 10th power is not a nicer number than 14 factorial. So you look at what you typed into the calculator and look at what the calculator spit out. I want the nicer one, right? So sometimes the nicer one involves you doing less work. I mean, sign up for that any day, right? So the second question is 5C0. For that, we would want to use, if we're doing it by hand, we would want to use the formula, which we kind of discovered on the previous page to be this one, but a nicer version of it is this one. Because that speaks in terms of N's and R's, right? So here's my N, and here's my R. My N and R's look almost identical, so I'm gonna fix that. And they both look terrible, so there's no clear winner there. Right, so 5 factorial over 0 factorial times 5 minus 0 factorial. Now, there's one fact that you'd have to know in order to make this work, and we'll talk about it in a couple of minutes when we get there, and that is that 0 factorial, this guy, is somehow equal to 1. Now, I'll show you why that works the way it does in a couple minutes. It's actually a riveting tale. Right? So this is the same as saying 1. So I can kind of cancel that out. 5 minus 0 is 5. So 5 factorial over 5 factorial. Anything divided by itself, whether it's factorials, permutations, combinations, think of the most complicated expression in existence, divided by itself, the result is going to be 1. Right? So that's what it would look like by hand. On the calculator, as you know, much simpler. Function NCR 5, 0 gives it to you right away. All right. But the lesson here is twofold. One, we got to figure out what that 0 factorial thing is all about. Like 0 involving multiplication. How on earth could that be equal to 1? That doesn't make any sense. So I'll help you understand that in a minute. But also a generalization. You might start wondering, well, wait a minute. If the R value is equal to 0 in a combination, is that always going to be 1? That's a hell of a question. And it's something that you can actually test out. If you have a suspicion when it comes to Desmos, you could always test it out using Desmos. So function NCR, just put in some dummy variable for the n value. Yeah, I mean, you can try to use n. Sometimes it doesn't work. But if I say NC0, it'll ask me if I want to create a slider for n, because I'm telling it that I want n to vary. I want that first value to vary, but the second value I want to remain at 0. So I'll add the slider here, and when I slide along, now permutations don't work for negatives. Permutations, combinations, factorials. You can't arrange negative items. You can't. I mean, we can try to arrange 0 items, but if you arrange 0 things, you get a break in the logic. So we only focus on positive values, and we only focus on whole numbers. So when you set up your slider, you might want to start it off at 1, make it some high number, and make sure that the step, which is the increments that it goes by, is going to be 1, so it only goes by whole number values. Now, you can start it at 0 too if you want. I mean, it really doesn't make a difference on the low end as long as you're excluding the negatives. Right? So slide along, and you could see no matter what value I put in here, I think I might accidentally type in 10 for this step. No, it's just maybe let me make that a little lower. So it's really kind of hopping around on it. But no matter what that high value is, that n value, the NCR is always equal to 1. Right? So there's no change there. Right? So we
can you explain why it doesn't change from 1 again?
Because the R value, if the R value is equal to 0, the combination is always going to be equal to 1.
Oh, okay. Thank you.
And philosophically, that just boils down to the idea that you're taking. So this is the 5-person classroom, right? So 5 people in the classroom, and I say, all right, I need none of you to go to the main office right now and get my mail for me. How many ways can that happen? You might look at it and say, well, there's no way that can happen. Well, I'd look at it and say, well, there's one way that can happen, because nobody leaving the room is the same as everybody staying in the room. And there's only one way that everybody can stay in the room. Right? They're all just staying put. I don't care about the arrangement. I care about the fact that this unique collection of 5 people are all staying in this room. Right? So that brings us to C, which is kind of the other end of that point. So by hand for C, it's the same kind of setup where it's like, oh, we got to get into this factorial business. 14 factorial over 14 factorial times 14 minus 14 factorial. So a lot of repetition here. But the computation part of it is really just to support our theoretical understanding. Because the 14 divided by 14, anything divided by itself is going to be equal to 1. But then you also have this part here that gives me a 0. So again, we're coming back to that idea of 1 over 0 factorial. And so far, we're taking it on faith. You're just believing me. That's an awful risk. You're believing me that 0 factorial is equal to 1, and I got to prove it to you, right? Which I am happy to do in a couple of minutes. But I'd also look at this and say, well, I got a 1 again. I want to make sure that that's going to happen, right? So the notation is getting across the idea that I have 14 people, and I want to create a group of 14 from those 14 people. There's only one way to do it. If I say, just kind of think of it this way. You're a tour guide, and you're taking the people that showed up for the tour onto, like you're going to take them around the museum, and you can only handle 15 people. Each tour guide is only supposed to take 15 people. You're like, okay, so I'm going to break you all up into groups. Let me just count you off. And I'm going to get 15 people with me, and I'm going to get 15 people with Maria. All right. So 1, 2, 3, 4, 5. Oh, there's only 15 people. All right. Well, you're all coming with me then. Or I need some time off. You're all going with Maria. I'm going to sit this one. Yeah. But if that's what the grouping calls for, and that's what the number of people are that are available, then that would just be your one group. Right. Now, if it were an arrangement, that's a different story. Then it would be like, okay, I got to line all these people up. How many ways can I line them up? Different conversation. But here it's just how many people are available. How many groups do I want? How does this work out? Now, when I pop this into the calculator, function, boom, 14, comma 14, still get the 1. You can play around with different values here. You can do the whole slider thing again. I already have a slider for n. So I can say n comma n. That allows for the first and second value to be the same. All right, so first and second value, in this case, I have it at 82. 82C82. Result of 1. 63C63, 1. 29C29, 1. 100C100, 1. Right? So it checks out no matter what the low value is, no matter what the high value is. If they're the same, it's going to give you a combination value of 1, which is very nice. Right? It's something that you can rely on. Right? So it kind of it streamlines things. Noticing those properties and those relationships goes a long way. Right? So I'm going to put stars on the next 2 questions for you to try on your own, but I do want to take you through the mysterious 0 factorial. Right? Because I can show you here. I mean, this is by no means a proof. It's just you believing somebody who's not me. 0 factorial is 1. All right, well, you believe me now because the calculator proved, like that's how it goes, right? Somebody else said the same thing, so it must be true. Yeah, no. So we need some more evidence here. So n factorial is equal to n times n minus 1 factorial. All right, where am I getting that from? I'll show you. Oh, I already shut them up. That's this general rule for factorials. We played around with this a little bit last time. Right? That's all I'm doing. I'm just kind of referring back to that. All right. So let's take a look. Oh, overshot the math. Now I could look at this a couple of ways. Since I'm looking for 0 factorial, I could do this. I could say, okay, well, I'll let n be equal to 0. So 0 factorial, off to a good start. 0 times 0 minus 1 factorial. Run into a little bit of a problem there, though, because negative values, when it comes to counting, has no meaning, right? So we're not going to arrange negative items. So this strategy or this approach wouldn't really work. However, if I go to 1 factorial, I'm going to kind of use a backdoor approach here. Right? So I'm going to let n equal 1. Right? So everywhere I see an n on the right-hand side, I'm going to replace with a 1. So 1 factorial we know is equal to 1. 1 minus 1 is equal to 0. And then by established properties of algebra, like identity and PEMDAS and things like that, we can say the right-hand side is just going to simplify down to a 0 factorial, which equals 1. All right, so we get a proof, we get evidence that 0 factorial is equal to 1, but in terms of an intuitive understanding, it's still kind of a little iffy. It's still kind of tricky because you look at it and say, well, yeah, but it's still got a 0. How can I arrange 0 things? It's the same way that I can send 0 people to the main office to get my mail. Right? If I have 0 things, I can only arrange them one way. Right? That is to say, well, here's my nothing. I have a nice arrangement of nothing. There's nothing to move around. Right? It's just a set of nothing. Right? But there's one collection of that nothingness. But it's really, again, more so like not so much what we're talking about, it's what we're not talking about. So when I say that I'm sending no people out of the classroom, that's saying that I'm keeping everybody in the classroom, right? So if I say that I have, like when you think of an arrangement, you might think of flowers, So if I want to create an arrangement, I want to create a nice bouquet, I want to create an arrangement of flowers, what I could do is I can go to the florist and I say, okay, you have all these wonderful flowers over here. I'd like to make an arrangement of those 5 different types of flowers, right? Then I realize I don't have any money. So what they can do is make an arrangement of those different flowers. I'm shit out of luck. So they get their flowers, I get nothing. The arrangement is still happening, but I get nothing out of it. So I have nothing to arrange, but they have everything to arrange. They're still going to make whatever arrangement they're going to make, but I have the nothing as a remainder, and there's only one thing that I can do. I am the one person with nothing, the one person. I got to take a hike. It's all over. Right? So that's kind of more of a philosophical way of doing it. If I say I have no idea what you're talking about, I really have one idea. Yeah, the one idea of the nothing that you understand that I'm talking about. Yeah, exactly. Very good. Exactly. So that's really the justification. For probability and counting specifically, it's a lot of mind-bending stuff. But if you can kind of come up with an example or a strategy or just kind of just a way of thinking about it that works for you, then that's the way to go. But what I just try to do is come up with all these different anecdotes and see what I can come up with. And see if I can get one that lands. On page 35, we got all these shortcut rules. They're wonderful, but again, they just kind of they're placeholders for what we do in the calculator. And we've talked about them all, so they're all there. It's just a question of just kind of making your peace with them. But then we get the applications, and I think time-wise, it's probably where we're going to end. Well, we'll see. May have to go a little bit further, but the shortcut rules here, they're wonderful. Like I said, you can use them, but you could also use the calculator. A good example here, you have find the probability that of 5 selected people, because we had to tie it with probability, no 2 share the same birthday. Right? So, and again, they're asking a question. We want to interpret that in a way that makes sense for the probability. So in A, they're really asking us the probability all 5 birthdays are different. Right? So if you're saying that no 2 people in the room, you have 5 people in a room, no 2 people have the same birthday, we're saying they all have different birthdays. So that's what we got to look at. We got to say that the first birthday is different from the second birthday, which in turn is different from the third birthday, which in turn is different from the fourth birthday, and followed by being different from the fifth birthday. Right? So you got to think about how people can have birthdays. Under what circumstances might a person have a birthday? Well, the first person, if you're looking at the 5 people, the first person can be born any day of the year without restriction. Right? We don't know what their birthday is, but we got to assume that they could be born at any time. So they have 365. We're just going to assume 365 to not get too complicated. They have 365 days to work with. Right? Any of the 365 out of the 365 are fair game for that person. The second person has the burden of not being born on the same day as the first person. So we have, again, this is the first person. This will be my second. And third, fourth, fifth, and so on. Right? So the second person, if they're born on the same day as the first person, then we fail. All right. So let's say the first person is born on January 1st. And we're not talking about like the year of birth, just the day. So that the second person could be born on any day other than January 1st, which means that they have 364 days to play with out of a total of 365. And there's still 365 days in a year. We got to look at it with replacement because it's not like we're removing days from the year. Those are still available because people still can be born on the same day. We're just looking for the cases where they're not. Right. So the third person can be born on any day other than the days that the first 2 people were born. So first person was born on January 1st. Second person was born on April 15th. Those are 2 days that are eliminated from the set of 365. So there's still 365 days available in the year, but the third person can only be born, if this is going to work, it can only be born on 363 of those days. Once you get a sense of the trend, you start realizing, oh, okay, we're just decreasing across the top and keeping the bottom the same. All right. So then when you look at this, it's not so much of recognizing keywords like like I was going to say permutation, but I mean arrangement or groupings or things like that. It's more so that you look at this and say, wait, this is a case where you have 5 slots and you're declining values starting with that high number of 365. That's what you do when you solve a permutation problem. So this is the same as 365 P5. Now you could look at that and say, all right, cool. Why would I have to write that? Couldn't I just multiply 365 times 364 times 363 times 362 times 361, get that answer and be fine? My answer to that is, well, look at the next problem. 45 people instead of 5 people. That's a lot of multiplying. So we definitely want a shortcut. Right? So then the bottom is just 365 being raised to the 5th power because it's an identical value being multiplied by itself 5 times. Right? Now, sometimes what I like to do is ask the question, instead of asking for a probability, I'll say, give me an expression that could be used to give the probability for the 10. So I wouldn't want the actual answer because sometimes the answer is just a nightmare. It's just hideous. Sometimes I just want this notation. If I do want the answer, I'll give you rounding instructions. I'll say round your answer to the nearest three significant digits, or I'll say simplest fraction form or something like that. I'll give you more of an indication. But if we do want to know, we can put it in the calculator. And I'm going to do, I don't need that, division, right, because it's a fraction. Then I go into functions, the NPR, 365, comma, 5. And then on the bottom, 365 raised to the 5th. And you can see here, we're looking at about 0.973. All right, now, logically, you just kind of play this out. You only have 5 people in a room. If I told you 5 complete random individuals, so complete strangers, they don't know each other, there's no affiliation whatsoever, just randomly selected individuals, put them in a room, and I said, hey, guess what? Chris and Josina have the same birthday. You'd be like, holy crap. You grab 5 random people and 2 of them have the same birthday? How did that happen? That's pretty lucky, or unlucky, depending on your feeling about that sort of thing. But it's not likely, so this 0.973, right, you got at least the quality of that number you should be feeling pretty good about. Yeah, it should be a high probability. Right? Now, if I told you that we had 1,000 people in a room together, and I told you that none of them had the same birthday, you'd be like, all right, something's wrong there. Like, you have that many people in a room and not one common birthday, somebody's lying about their birthday, right? Because after you hit the 365th person, you'd have to have some overlap. Because let's say the first 365 people all have different birthdays. Every single one of them somehow has a different birthday. The 366th person, their birthday has to match with one of those 365. So there is a declining probability as you increase the number of trials. So when we get to the next example, you'll see, oh, all right, the probability is going to change. It's not always going to be a high probability, but you can tie your common sense to it, because that's part of the fun when it comes to probability. You're like, oh, this answer makes sense. This answer doesn't make sense. Why? Because that's not how the world works, So in part B, where it says probability at least 2 share a birthday, right? So I'll write it as opposite of our answer for A, right? Because if we're looking at in A, all the birthdays are different, then in B, when it says at least 2 share a birthday, that means that maybe exactly 2 people have the same birthday. Maybe 3 out of the 5 have the same birthday. Maybe 4 out of the 5. Maybe all 5 of them have the same birthday. That would be shocking, but you think something was up if that happened. But bottom line is, it would have to be the opposite of all the birthdays being different. So this one, once you read into it a little bit, you don't really need a formula. You just look at this and say, okay, 1 minus 0.973 is 0.027. So then you kind of start looking at this and say, okay, well, in number 7, this is exactly the same question as number 6, except it's 45 instead of 5. So why not take my answer, what I did on the Desmos calculator, and just tweak it a little bit? Right? So change my 5 into a 45. So this is the equivalent of part A in number 6, where it would be all 45 individuals having different birthdays. You tell me that there's 45 people in the room and they all have different birthdays, that's definitely going to be less likely than only 5 people in the room having different birthdays. The more people you have in the room, the more likely they are to share a birthday, still not guaranteed to happen or impossible to happen, but it's getting closer and closer, right? So subtract this from 1, and we see now that we're looking at, and I could just kind of pop this in there. Little things in life. Oh, that little stray mark is going to kill me. I got ways. Got ways to handle it. Got to break out the old white pen. No. That's essentially talking about the same idea, right? But much lower probability because, I'm sorry, much higher probability than the 0.027 because the likelihood that there's going to be a common birthday is a little bit more pronounced. Now, if you want to get a little bit more crazy with this, you can do what we did before and just create some dummy variable for the bounds. I'm sorry, dang it. And create a slider so that you can see what's going on with those probabilities as you increase the number of trials, increase the number of individuals in the room. Right? So I want this to go away. I guess I got to live with it. Right? So I can slide my slider, make it start at 0, go to 400, only go by ones. But you can say, so 5 people in a room. If I can get it to land on 5, it doesn't want to. All right, well, 6 people in a room, very small. 45 people in a room, that's my 0.94-ish. It's getting larger and larger. When I get to 100 people in a room, it's almost 1. Then it says undefined because it just, the numbers got so huge that it just gave up because it's trying to compute 365 raised to the 155th power. So it's just given up. But it's at a certain point, it's like, well, yeah, I'm not going to do the math, but yeah, it's 1. Once it hits over 365, it starts recognizing it as, all right, well, it's a certainty now. The numbers are large enough. Do you have to do it with the Desmos? No. You can crank it out, manually, but sometimes doing stuff like this is useful because, and I've been mentioning this in all my classes, you do something like this for one of the problems that we do here, and then you save it, and you call it birthday problem. I got a lot of extra stuff here that I don't really need for the birthday problem, but I can trim all that stuff out. I mean, I got a lot of stuff that I don't need, but trim all that stuff out and save it so that when you come across a question like this, if you do, no hint there, you're totally coming across questions on a test, then you have, you have it set up and ready to rock and roll. So you save it, call it the birthday problem, like I said. And then when you go to do it on a test, you have something ready to rock and roll that you can use. You can use it as a reference. All right. Oh, a different answer on Desmos. Okay. So it depends on how you typed it in, but if you typed it in the way I did it, you should have got the same answer. So it might be a matter of maybe just using a different function. This should be a permutation, so hopefully you weren't using a combination. That would be a reason why you would get an error. But I'll just do it again really quickly so that we can just make sure that I didn't screw it up. But for 6a, it's function NPR 365, 5. and then 365 raised to the 5th. Right, so that was my part A, and then I just tweaked it by subtracting from 1, and that gave me my part B. I did a little funny rounding though. Actually, that should be a 0.0271. Right, I'll do it a different way really quickly. So as a fraction, if you didn't like the permutation approach, you can do, it might take a little while, but, in the absence of a better alternative, then, this is what you do. 1, and then 365, and just 5 times. And so you can get it that way. But again, that little adjustment of subtracting it from 1 makes all the difference. Right. And then, so what I was mentioning before is that if you were to do this for 45 selected people, obviously you don't want to do it this way. It would take a while, at least not on purpose. If you're stuck doing it that way because you don't remember how to do it with the permutations on a test, yeah, start typing, 365 times 364, keep going until you use 45 slots. You'll get the right answer. It'll take a little while, but you'll get there. And then you'll be good to go, right? But yeah, now the other one, it was 1 minus the fraction NPR 365 45, and then 365 raised, not divided by something, raised to the 45th power. And so that's where that decimal comes from. Right, so hopefully that helps. So let me stop this video.